Good afternoon, ladies and gentlemen. The topic this afternoon is binary logic and the Boolean algebra. Let's begin by looking at this interesting statement about binary logic. There are only 10 types of people in this world. That is, those who understand binary and those who do not understand binary. Yeah, the statement doesn't seem to make sense to those who do not understand binary. But I believe by the end of this topic, we'll be able to make sense out of this statement, which seems ambiguous to some. Okay, let's move. Let's look at binary logic. Binary logic deals with binary variables that take two discrete values, that is 0 and 1, and with logic operations. So the three basic logic operations are the AND, OR, and the NOT. AND, OR, and NOT. Then binary or logic variables are typically represented by letters A, B, C, or X, Y, Z, etc., depending on the number of variables that are being considered. So let's look at the binary logic function. Yeah. The binary logic function takes the form f, then in brackets you have binary variables is equal to the expression. So in the brackets on the left-hand side of the equal sign, you have a set of binary variables. Then on the expression side, this is where you have the operators, which are the plus, the dot, and the complement, which we normally call the bar. Then you have the constants, the 0 and 1. Then the groupings in parentheses. Okay, so these statements are very, very important in helping us understand the expression of the binary logic function. Let's look at a typical example of the representation of a binary logic function. So we have f, then in brackets a and b. So a and b here are variables or binary variables. Then on the right-hand side of the equal sign, we have the binary expression. This is an expression. So this is the general representation of a binary logic function. So we have the first example is f a b with two variables a and b, and you have that expression. Then the second is g, then in brackets x, y, z. So there are three variables here. Then on the right-hand side, we have that expression. Okay, let's now look at some basic logic operators. These are very, very important. We need to pay extra attention on these basic logic operators, because everything else that we are going to discuss will be built on just these basic logic operators. So the basic logic operators are three in number, which are the AND, the OR, and the NOT. The AND, the OR, and the NOT. Then down here we have their representations. So we have f, a, b, which are the variables, is equal to a dot b. So the dot here represents the AND. Okay, so f, the function f is equal to 1 if and only if a and b are both equal to 1. Shortly we shall explain what this means. Then we move to g. The function g, where the variables are a and b, is equal to a plus b. So the plus in this statement or in this expression represents or. So a plus b means or. So for this expression, the function g is equal to 1 if either a or b is equal to 1. So when one of the two or both are equal to 1, then we are going to have g being equal to 1. Then we come to h. H is simply an inverter. H is an inverter. So like in this case, on the left-hand side of the equal sign, we have A. Then on the right-hand side, we have A prime, which is typically supposed to be A bar. A bar means an inversion of what was put in. So if the input is A, then what comes out will be A bar. If the input is A bar, then what comes out is A. So in other words, this expression or this operation is simply inverting. So this inversion operation is what we call a NOT. So now let's try and explain what in detail what each of these is. So we begin with the AND. So to understand what this AND is, let's look at a simple illustration. This is an illustration of a basic electric circuit. So let's look at the basic electric circuit. This electric circuit will comprise two switches connected in series. Two switches connected in series and controlling a lamp. So let's call this lamp F. So we'll call the lamp F. Then we have the input V. Yeah. So this is the supply voltage, and we are for illustration purposes we are using DC just for our understanding. Then the first switch, let's label it A. The second switch, we're going to label it B. Okay. So now, from our knowledge of the behavior of electric circuits, without doubt, we know that for the lamp F to come on, both switch A and switch B have to be closed. So both switch A and switch B have to be closed. So you've seen the connection here. This is the reason why this operation is known as the AND. So let's get back here. So we're saying F with A and B as the variables is equal to 1 if and only if A is equal to B is equal to 1. So now let's try to explain what is meant by 1. Okay, so in logic um, uh, mathematics, we refer to the on state of a switch. The on is referred to as a 1. Sometimes we call it high. Sometimes we call it high. High also refers to 1. Then we may also use the term closed. Closed. Closed also refers to 1. So in this topic, we'll basically be looking at two constants, a 0 and a 1. This will be all we'll be discussing. Everything will be pivoted around a 0 and a 1. So on, high, closed refer to 1. Then off, low, and open. These will refer to 0. So on, high, and closed is referred to as a 1, whereas the off, low, and open is a 0. So let's understand something about the behavior of this circuit. We've already named it the AND, because for the lamp F to come on, it will require that both switch A and switch B are closed. Now, let's look at other possible combinations of these two switches. Let's draw a simple table here. Let's illustrate by using a simple table. Okay, so we have the variables A, B, and the F. So let's start with some the basic condition that we may take. Before we close any of the switches, we expect that the two switches are open. So if the two switches are open, they are indicated by zeros. So we have 0, 0. So 0 here and 0 there, meaning both switches are open. When both switches are open, the lamp F will not come on. And when it doesn't come on, it means it's in the off state. And when it is off, we represent it as a 0. Then, if let's say we leave the first switch off and we switch on the second switch, we leave A open and close B. The lamp F will still not come on. It will still be a 0 because the circuit is not complete. Now, if we decide to close the first switch and open the second switch, what do we expect? Still, the lamp will not come on, to be off, because the circuit is still not complete. But when we close the first switch and also close the second switch, we expect that the lamp will come on. So this is the behavior. So we have 0, 0 will give us 0, 0, 1, 0. 0, 1 will give us a 0, then 1, 0 will give us a 0, 1, 1 will give us a 1. So such a table that gives us more information about the behavior of a logic operator when subjected to different input combinations is known as a truth table. A truth table. We shall explain more about a truth table in the coming slides. Okay. So now let's try to make ourselves understand this notation here. So now we've made it clear that for the lamp F to come on, switch A and switch B have to be closed. So the notation now for the AND, looking at what we've explained here, we can basically say F will give an output uh, regardless of whether it will be low or high. When you have this notation, A, the AND is denoted by a dot B. So F is equal to A dot B. So F is equal to A and B. So the behavior here is such that it tends to simulate two switches connected in series. So if we had more than two variables, still it would mean that same number of switches connected in series and controlling a lamp. Okay, so this is the AND operation. Now let's move to the OR operation. The OR operation. We'll also use a basic electric circuit to explain the OR operation. Let's get rid of these red. We discard the writing so that we start all over. Okay, let's look at the OR operator. So for the OR operator, we'll still use a basic electric circuit. So we have a simple circuit controlling a lamp. Oh, controlling this is something. Okay, don't worry about the rough drawing there. It's not easy to to come up with a good drawing using mouse. Okay, so for the OR operator, we consider two switches connected in parallel and controlling the lamp labeled G. So we are looking at this expression now. G equals A plus B. So what we have here is a voltage source, and we have two switches controlling lamp G. So from our knowledge of circuits, we can tell that the lamp G will come on when either switch A or switch B or both switches are closed. Okay, so lamp G will come on when either switch A or switch B, or both switch A and switch B are closed. This is a fact. I think we can tell just by visual inspection. We can tell the basic operation of this circuit. Okay, so in the logic operation would express this statement as A, where there's O, we put a plus B. So we'll now generalize it as G, which is the output. The output is the lamp when you look at our circuit. So G is equal to A or B. So the plus is representing OR operation. Okay, let's now look at a simple table that will make us understand how this circuit will work, considering different input combinations. Okay, so we have the two inputs which are A and B. Then we have the output, which is a G. So let's look at the different input combinations. We mentioned what zeros and ones mean. So when the switch is on, just a reminder, when the switch is on, we denote it by a 1. And when the switch is off, we denote it by a 0. So let's look at the different combinations here. So first combination is where both switches are open. When both switches are open, we don't expect the lamp G to come on. Then when the first switch is open and the second is closed, we expect the lamp to come on. And when the first switch is closed and the second switch is open, we expect the lamp to come on. And when both switches are closed, then we expect the lamp to come on. So this is the behavior of an OR logic operator. This is the behavior. And a table such as this, that is helping us to understand the behavior of this circuit when subjected to different input combinations, is known as a truth table. So this is the truth table for the OR logic operator. Okay, I hope this is clear. Let's move now to the NOT logic operator. We move to the NOT logic operator. So for the NOT, we shall still look at a basic electric circuit. So here's the electric circuit. Have the source there in that direction. Then the other side grounded, and we have a lamp there. Then somewhere in the middle, we have okay. So this is A, and this is A bar. Okay, so let me also make one thing clear here. In these slides, you will notice that an inversion is being indicated by a prime. So in most literature, and had we been using the whiteboard, we were going to use this notation, a bar with a line on top. So both this first case and the second mean inversion. Okay, so instead of having a line drawn above a letter, we are simply using a prime. So when we see a prime in this lesson, know that it is an inversion of a bar. So we have A here and A bar on the lamp side. Okay, and by the way, a word of caution, this is just for illustration purposes. Don't try this at home. This is likely to cause a serious problem because it's a serious short circuit. This is just for illustration purposes, for theoretical illustration. You do not need to do this practically because it will cause a very serious problem. Okay, not to be do not try. Let me just write something in case what I'm saying is not clear. So do not try this anywhere, whether at home or at the lab. Don't try this circuit. Okay, now let's look at the operation. Let's say we've connected the supply to this combination. We have a lamp, then between the lamp and the supply, there's a push button. So when the push button is open, we expect that the lamp will come on. Then the moment you press to close the push button, it means you create a short circuit. And that short circuit will mean that all the current that was flowing through the filament lamp, it will no longer go there, but it will choose an easier path here. So it means you have shorted out the lamp. By pressing the push button, you've shorted out the lamp and the lamp will go off. So in such a case, let's try to draw a table to perhaps help us understand what it means by the shorting. Okay. So this, the A bar, we can actually call it H. They're using the letter H here. We're using H. Okay. Let's label it H. Okay. Now this is a push button. Okay. So let's consider the first case. The first case, switch A or push button A is left open, and when it's left open, we denote it by a 0. And when it's left open, it means that the lamp will come on. The lamp here will come on, so it will give us a 1. Then when we close the push button, we give it a 1, it means the lamp will not come on because it will be a short circuit. All the current will pass through the switch and it will not have to go through that high resistive path. Okay, so we've noticed that this circuit is simply changing the status of the input. So if the input is a 0, then what comes out is a 1. If the input is a 1, what comes out at the output is a 0. So it inverts. So this then is the behavior of a NOT gate. So a NOT gate will simply change the status of its input. If the input was a 1, then the output will be a 0. Yeah. Okay. Now, let's look at, we've looked at the behavior of these three basic logic operators. Now, let's consider their symbols. The AND operation, or the AND logic operator, is denoted by this symbol. It's the symbol. So we have A here, and B here, and F here. So this F is the one where we illustrated as being A dot B. Then we come to the O. The O is similar in appearance to the AND, but it has some kind of a depression at the input side. So we have the A, the B, then we have the G. So this G is just A plus B. Okay? Then the third one, the knot is simply a triangle-like shape with a circle at one end. So if you have A at the input, then what comes out is A with a bar. So this is basic logic operators. So I guess we now have the foundation to proceed in this topic. Let's move to the next slide. So the basic logic operators still continues on this slide. So one-bit logic AND resembles binary multiplication. Okay? That's what we are looking at. This symbol A, B, then we have F. So whenever we see this symbol, let's remember two switches connected in series. Let's remember two switches connected in series. So we've illustrated several times now that this is A dot B. Now let's now that we have this symbol as well as the circuit in mind, let's look at these operations here, the four basic operations that are connected to the AND. So let's consider the circuit that we looked at on the previous slide. If the first switch is open, the first switch is left open, and the second switch is also left open. Because it's actually this notation we are considering. The first switch is left open, and the second switch is left open. What do we expect on F? We expect a 0. The lamp will not come on when both switches are open. So now let's consider the second case. Okay, so this is simply deriving its concept from this general expression. So let's move to the second. If the first switch is closed and the second switch is left open, do we expect the lamp to come on? No, it won't come on because the switches are connected in series. The circuit will not be complete, so we expect a 0. Then, if the first switch is left open and the second is closed, still we won't expect anything because the circuit is still not complete. But when both switches are closed, then we expect an output. The switch will come on. So the dot here indicates AND. So now you've noticed that this AND operation resembles very much binary multiplication. So if you multiply 0 and 0, you get a 0. You multiply 0 and 1, you get a 0. You multiply 1 and 0, you get a 0. Multiply 1 and 1, you get a 1. So this is what this statement implies. Okay, let's move to the OR operation. So the OR here, we're saying it resembles binary addition, except for just one operation, which we're going to explain. So for the OR, let's remind ourselves, we said this was the symbol. Yeah. So we have the G there. Then A, B. So when we look at this symbol, let's remember two switches connected in parallel and controlling a lamp. And we mentioned to say the lamp will come on when either of the two switches is closed or when both switches are closed. But when both are open, we will not see an output. So in that case, it actually implies that, okay, let's put the general expression. The general expression here is A plus B. So the plus denotes the OR operation. So if switch A is left open and switch B left open, we don't expect an output. But when switch A is left open, whereas switch B closed, we expect an output because the circuit will be complete through one switch. Then if we close the first switch and open the second, still the circuit will be complete. We'll be able to see an output. And if we close both switches, we'll be able to see an output. So now let's look at its resemblance with binary addition. When you add 0 and 0, definitely you get a 0. You add 0 and 1, you get a 1. You add 1 and 0, you get a 1. But when you add 1 and 1 in the binary system, you don't get a 1. Instead, we get a 1, 0. But when we are dealing with basic logic operators, we get a 1. So a 1 is simply here implying high, not necessarily the sum the sum of two bits, but it's a logic operation. So the 1 here implies high. Okay, let's move to truth tables for logic operators. We've already actually introduced truth tables. We talked about them on the first slide. So a truth table, this is a tabular form that uniquely represents the relationship between the input variables of a function and its output. Okay, let's make a small change here. Okay. All right. Okay. So it represents the relationship between the input variables of a function and its input. And these combinations are very, very important. If we understand the various input combinations of variables and the kind of output that we expect, then we'll be right to work out any problem that we're going to encounter in logic operations. Okay, let's look at the two input AND. So the two input AND behaves as follows or as shown. So if the two inputs are the two switches, you think of an AND as two switches connected in series. So two switches are open, we expect nothing on the lamp. And when one switch is open and the second switch is closed, still won't see anything. If the first switch is closed and the second is left open, we won't see anything. But when both switches are closed, that's when we'll see an output. Okay, so this is a two input, and we've already illustrated these things. And let's look at the two input OR. For the two input OR, the inputs are A and B. So OR implies two switches connected in parallel and controlling a common lamp. So when both switches are open, we don't expect anything, but whenever one of the switches is closed or both, then we expect an output. So we have 0, 1, 1, 1 as the output. Then a NOT simply inverts what was given at the input. So if at the input we give a 0, then we expect a 1 at the output. If we give a 1, then we expect a 0 at the output. Okay, so these are the truth tables for the basic logic operators. Okay, so now there's this important statement that we need to remember. If a function f depends on n variables, okay, if a function f depends on n variables, then there are 2 raised to the power n rows, 2 raised to the power n rows in the truth table, since there are 2 raised to the power n possible binary combinations for the n variables. So we'll be able to tell the possible binary combinations given the number of variables. So from the number of variables, it's very possible to tell the possible binary combinations or the number of possible binary combinations. Okay, let's now look at logic gates. We've actually already highlighted something on logic gates. So logic gates are simply abstractions of electronic circuits, circuit components that operate on one or more input signals to produce an output signal. So these are abstractions of electronic circuit components that operate on one or more input signals to produce an output signal. So these are basically the building blocks of electronic circuits. Logic gates are the building blocks of digital electronic circuits. Okay, so the two input AND is represented as follows. We've already talked about this symbol. this is the symbol for a two-input AND get. These are gets, yes. So A and B are the inputs, and F is the output. So the second is the two-input OR, where A and B are the inputs and G is the output. Then we have the NOT, which is also known as the inverter. The input is A and the output is H, where H is equal to A bar. So this get inverts the input. You put in a 1, it takes out a 0. You put in a 0, it takes out a 1. So that is what this get does. Okay. Let's look at the timing diagrams. These are very, very important in the analysis of logic and operators. Okay, so let's look at the input signals, which are A and B. This is the waveform. This is the waveform for the B, the waveform for the A. So now we are looking at 3 different gets. There is the AND, the OR, and the NOT. So let's first look at the AND. So for the AND, we know to say the output will be high only when both inputs are high. That's the condition. So whenever the inputs are different, the output will be low. Whenever the inputs are different, the output will be low. Whenever the inputs are 0, the output will be low. So we only have a high output when both inputs are high. That is for the first get, the AND get. So let's look at the input signals. So signal A is high from 0 to 1, whereas signal B is low from 0 to 1. So we don't expect F to be high. So high, F is low here, up to 1. Then let's move now. From 1 to 2, we've noticed that the signal A transitions from 1 to 0, whereas signal B still remains at 0. So now between 1 and 2, both signal A and signal B are 0. So we don't expect any rise in the signal at the output. Then we come to the period from 2 to 3. From 2 to 3, signal A is still low, but then at 2, signal B transitions from low to high. So then we have signal A being low from 2 to 3 and signal B being high from 2 to 3. Then at 3, we notice that signal A transitions from low to high. That is at 3. And meanwhile, signal B is high at 3. And it remains at high up to 4. So now, signal A just transitioned from low to high, and it remains high from 3 to 4. So if we look at the output, from 3 to 4, both signal A and signal B are high. And because both signal A and signal B are high, then we expect an output to be high. So this is the reason why we have a high. Then again at 4, signal B transitions from high to low. So by signal B transitioning from high to low, it means that the input signals are now different. So different input signals means that the output will go back to low, and it continues to low up to the end of our timing. Okay, let's now go to the OR. The OR, if we remember, it gives an output whenever one or both of the switches is closed. So let's look at the combinations here. So we're looking at the second output waveform here. So signal A is high from 0 to 1, and signal B is low from 0 to 1. So we expect that G will be high from 0 to 1. Then signal A transitions from high to low at 1, meaning that from 1 to 2, we'll have signal A and signal B both being low. So because both A and B are low, then G will also transition at 1 from high to low, then B on the lower side from 1 to 2. Then if we go to the input signals, at point 2, we have signal B transitioning from low to high. So meaning that signal B will be high between 2 and 3, when signal A will be low between 2 and 3. So since one of the two signals is high, then we expect that the output will be high. So if we follow from 2 right up to 6, the input combinations are low, high, high, low. So whenever the inputs are different for an OR operation, we expect that the output will be high. Okay, then let's move to the third logic operator, which is a NOT. So a NOT will simply invert. So in this case, we are looking at signal A. Signal A is the one that is being considered. And a NOT gate always has one input and one output. Okay, so if we look at signal A, from 0 to 1, it's high, meaning the output will be low from 0 to 1. Then at 1, it transitions from, signal A transitions from high to low. The moment signal A transitions from high to low, then the output will transition from low to high. Then from 1 to 3, signal A is low, and the output from 1 to 3 is high. Then at 3, there's a transition on the input signal from low to high. Then it remains high up to the end of our timing point. Whereas on the output, at 3, it transitions from high to low, and it remains there up to the end of our timing point. Okay, so these timing diagrams are very, very important. We need to master these timing diagrams, as they are very, very important in our study. So there is a simple assumption to these timing diagrams. And the assumption is that the time that is taken for signals to propagate through these gates from the input up to the output is not being considered. So we are assuming that the moment an input signal appears, almost instantly the output also appears. We are ignoring what goes on, the switching process that goes on inside a gate. So this is the basic assumption that is here. Okay. We move to combinational logic. So combinational logic circuit is derived from a logic function. So let's consider the function here. We consider the function A bar plus B C bar plus A bar B bar. Okay. A combinational logic circuit can be constructed to implement F by appropriately connecting input signals and logic gates. Okay, so let's look at these three areas. Circuit input signals, that is from function variables A, B, C. This is what you follow when coming up with a combinational logic circuit. So circuit output signal, which is the function output, the F, and then logic gates. These are got from basic logic operations. Now let's look at what is happening in this circuit. So we have three inputs. There's A, B, C. The order doesn't matter there. So let's look at input C. Input C is fed to a NOT gate. So at the output here, we expect C bar. Because this is an inverter. It's simply inverting whatever is being fed into it. Then we have A. A is also being fed into an inverter. So at the output of the inverter, we'll have A bar. Equally B. B is being fed to this inverter. So we'll have B bar as an output to the third inverter. Then at the same time, from this B, we are tapping an input. So at this point, we still have a B. So we look at this AND gate now. This AND gate. So this AND gate has got two inputs. It has B and C bar. So we expect that the output here will be B, then dot C bar. Okay, B dot C bar. And meanwhile, this B dot C bar is an input to the very last OR gate, a 3-input OR gate. Okay, let's first finish these gates on the second stage. We are done with the NOT gates. Now we are in the AND gates. So for this AND gate, we are tapping one input from that A bar, and the other input is the output of this NOT gate, which is B bar. So we expect that the output here is going to be A bar, B bar, A bar, B bar. These are the combination of the outputs for the two AND gates. Then, since we've got the combinations for these two AND gates, it means we've automatically got the two of the three inputs to the OR gate. So the third input is coming from the middle NOT gate, which is A bar. A bar. Okay. So here now, let's look at what will come out. This is a 3-input OR gate. The behavior is just the same as a 2-input OR gate. So the first, we simply OR all these inputs. They have to be ORed. And remember, OR is represented by a plus. So the OR is represented by a plus. This is an OR. So F will be equal to, we have A bar, which is this middle part, or we start from the top, B C bar, another OR A bar B bar. So this expression, this expression is exactly the same as what is being considered there. So this is how this expression was arrived at. But this is not to say this is all there is. We can simplify this circuit further so that we have fewer gates. Because what it is in combinational logic is that you need to come up with a circuit that is as simplified as possible with the smallest number of gates possible. If you can reduce it, the smaller the number of gates, the better, because that also reduces the propagation delay, that time that is taken for the signal to move from the input to the output. Okay. Let's look at still on the combinational logic circuits derived from a logic function. So in order to design a cost-effective and efficient circuit, we must minimize the circuit's size and propagation delay. Yeah, this one we've already explained it. Propagation delay is simply the time that is required for an input signal change to be observed at the output line. So when you give an input signal, that time that will be taken for an output rather to be seen is known as the propagation delay. Then, like from this truth table, we can observe the results F is equal to A bar plus B dot C bar plus A bar dot B bar, and also G is equal to A bar plus B C bar. So these two expressions appear different. So there is an expression F is equal to A bar plus B C bar plus A bar B bar. And also G is equal to A bar plus B C bar. These two appear different, and yet on the truth table, they are giving us exactly the same results. Okay? They're giving us exactly the same results. But in appearance, they are different. So from the approach, you can actually get different results in this topic. So don't copy what your friend is doing. Just go your way, and you never know, you may be the person who is right. Because most answers in this topic are not unique. Yeah. So you may have different answers, but you should still be able to produce the same results when you come up with a truth table of your circuit. Yeah, the outputs should be the same for the various input combinations. Okay, so if you have the same input combinations, you expect the same outputs despite the expressions looking different. Okay, so truth tables for F and G are identical, meaning these two are actually the same function. So use G to implement the logic circuit. Okay, so implementation. Let's look at this circuit. This is the circuit we just looked at. So simplifying this circuit further, we come up with this circuit here. So let's see how this circuit was, let's look at the output of this circuit. Okay? This one we already generated it. Okay, we'll begin with C. C through the NOT gate. This gives us C bar. Then here we have B. So B and C bar will give us B, C bar. Then A through the NOT gate, the output becomes A bar. So now from here we are okay. We can now just add up the input, since this is an OR gate. So the first input is A bar. So this is being ORed with B, C bar. Okay, so this is actually the same as the circuit we just saw. This one, the expression rather. The G is equal to A bar plus B, C bar. Okay, this is exactly the same. Okay, I hope this is clear. Now let's start Boolean algebra. Boolean algebra is a powerful tool that is used to manipulate or simplify Boolean expressions. Yeah. These Boolean functions emanate from Boolean algebra, a concept that was proposed by George Boole, who lived between 1815 and 1864. This was in a publication known as An Investigation of the Laws of Thought. So the important terminologies in this discussion include literal, which means a variable or its complement. Then there's also the product term. The product term refers to variables that are connected by the dot. The sum term refers to variables or literals that are connected by a plus sign. Okay, let's look at some of the properties of Boolean algebra. So let x, which is the Boolean, be the Boolean variable. So x is a Boolean variable. Then 0 and 1 are constant. So we assume x to be a Boolean variable, then 0 and 1 to be constant. So whenever we see a plus, let's know that, or let's remind ourselves that we are looking at an OR logic operator. Then the dot is an AND logic operator. That information is very, very important. So let's think of this expression as an OR logic operator. Okay? Or simply an OR gate, the logic gates that we just discussed. So if the input, one of the input terminals is fed with signal X and the second is fed with a 0, it means that the output will be dependent on the type of signal that is fed on X. So if the x is a 0, then the answer will also be 0. So if and if the x is a 1, the answer will be a 1. So this is the implication. Let's put a circuit here. Maybe this will make us understand. We put a logic circuit actually. Okay. So let's say this is x and this is a 0. So x is one of the inputs, or 0, like this. So if x is 1, then we expect that the output will be a 1. If x is a 0, then the output will be a 0. This is what is meant here. Then we come now to the AND operation. Where there's a dot, we mentioned it's an AND operation. So for the AND, let's remind ourselves of this symbol. So we have x and a 0 here. So x and a 0 means we have x dot 0, x dot 0. So we mentioned for this operation, you say whenever one of the inputs is a 0, whenever one of the inputs is a 0, then the result will be a 0. Actually, this operation we're talking about now is here. We're not following the order, let's say. So when one of the inputs of the AND gate is 0, then automatically the answer will be 0. So we move to the next. If now we say one input is an x and the second input is a 1. So if one of the input is x and the other input is a 1, then the answer will be dependent on what we feed on input x. If we put 0, then the answer will be 0. If we put a 1, the answer will be 1. Okay, so this is where number 2 comes in. Then we now go to number 3. Number 3 is an OR operation. So for an OR operation, we have x here and a 1. So for an OR operation, as long as there is a 1 appearing, then know that the answer will be 1. As long as there is a 1 appearing in an OR, then know that the answer will be a 1. Okay, so these are some of the basic Boolean properties. Let's continue with some more properties. So for the fifth one, we have the input x and x. So x and x, the same input, the answer should be x. So if the inputs are 0, 0, then the answer will be 0. If the inputs are 1, 1, then the output will be 1. Then we come now to the AND. So if the inputs here are 0, 0, then we expect the output to be 0. If the inputs are 1s, we expect the output to be 1. Then we come to the 7th. The 7th, whenever the inputs are different, we expect the answer to be 1. That is for the OR operation. Whereas for the AND operation, whenever the inputs are different, we expect a 0. Then number 9, when we invert an already inverted signal, we are simply having the two inversions cancel each other out. What we mean is this: if you have x bar and you put another bar on top of a bar, this means the two bars will cancel each other out. Okay? So before we go to the other property, let's talk of the names of these properties. So the first property we looked at, the x plus 0 is equal to x, this is known as the zero action. Whereas the x dot 1 is equal to x is the unit action. And the x plus 1 is equal to 1, the unit property. Then x dot 0 is equal to 0 is the zero property. So this continues to property number 5, idempotence, then idempotence still, then complement number 7, complement number 8, and involution number 9. Now, let's move to the next property, which is known as the duality property. The dual of an expression is obtained by exchanging a dot and a plus sign, or a 1 and a 0 in it, provided that the precedence of operations is not changed. Then another condition is that you cannot exchange x with x bar. Now, let's try to illustrate what is meant by the duality property. So, with respect to duality, identities 1 to 8 have the following relationships. So, number one is related to number 2. Sorry. Property number 1 here is related to property number 2 by simply having this is the dual 1. This is the two things that have taken place here. The first one is the plus sign has been changed into a dot, and the 0 changed into a 1. The rest remain the same. That's the dual property there. So number 2 is the dual of number 1. Then we come to number 3. Number 3 is a similar case. So number 4 is the dual of 3. Equally, number 6 is the dual of 5, and number 8 is the dual of 7. Now let's see the relationship. Then for 3, we've seen that there is still x, not x, but the plus sign rather. The plus sign converted to the dot. The plus sign converted to the dot, and the 1 converted to the 0. Okay? The 1 converted to the 0, and the 1 at the output converted to the 0. So there are 3 changes that have taken place here. Then we come to number 5. Number 5, there's only one change. The plus sign changed to the dot. We come to number 7. Number 7 equally, number 7 has 2 changes. The plus sign changed to a dot, and the 1 change to a 0. So number 2 is the dual of 1, then number 4 is the dual of 3, and number 6 is the dual of 5, and number 8 is the dual, or number 7 is the dual of 8, or number 8 is the dual of 7. Okay, so this is the duality property. So let's continue and look at more Boolean algebraic properties. So still here, we shall consider x, y, and z to be the Boolean variables. Yeah, here we're talking of 3 variables. So we continue. On the previous slide, we ended at number 8, so we continue with 9 here. So Boolean variables, they obey the commutative law. So if you have x plus y, this is just the same as y plus x. Then you go to number 10, even for the AND gate, x dot y is the same as y dot x. Then we come to associative. So if you, the associative law applies to Boolean algebraic expressions. Okay, as it can be seen here, this is quite clear. Then distributive law also plays a very important role in Boolean algebra. So like the first one here, you expand out the brackets, x multiplies by y and x multiplies by z. That's how come it's like that. Then on the 14th one, still under distributive, expanding out this expression would mean x plus y in brackets dot x plus z in brackets, which is what is happening here. This is the distributive law. Then we come to the De Morgan's laws. These are extremely important laws that are used in the simplification of Boolean algebraic expressions. Let's look at number 15. Yeah. Number 15, let's write it down somewhere here. So we have x plus y, x plus y in brackets. Then we've seen outside the brackets there is this prime. That prime implies that everything is inverted. So x plus y inverted in the De Morgan's laws, this means you have x, then the plus is converted into a dot, and you have y. Then what happens? We had a long bar here covering everything. But the moment you change the plus to a dot, this long bar is broken and you have those bars appearing. That's how come we have that statement. Then number 16. Number 16 is x dot y in brackets inverted. So x plus y inverted, this means in the De Morgan's laws, the dot will have to be converted into a plus. So we have x plus y. Then this long bar that is appearing above these two variables will be broken. So we'll have a bar on x and a bar on y. This is what is happening on property number 16. So the illustrations down here are just bringing in more general terms where you have more variables being considered. Like the first one here is considering x1, x2, right up to xn. Then the inversion of that would mean having different, the same number of inputs rather, then with a broken bar on top, a bar appearing on each of the variables. Yeah, equally for the second expression. Okay, a long bar broken down. Okay? So understanding property 15 and property 16 will make it very easy for you to understand what is happening here. Yeah. Let's move to the absorption property. For the absorption property, we have x plus, then x dot y is equal to x. So whenever you have variables that are of this combination, know that the answer will just be x. X plus xy is equal to x. Then using the duality property, you find the second expression, which is x dot, where the plus is converted into a dot. So the plus converted into a dot, but it gives still the same answer. So this dot converted to, was just converted from a plus, equal this plus just converted from a dot. So let's prove the first property. Let's prove it. So step number one is to expand out this expression. So this x is not alone. There is a 1. There can be a 1. Just for the sake of expansion, there can be a 1 here. So now, if we factorize out the x, we'll have x dot open bracket 1 plus y, close the bracket. Okay? Then, this is x dot open bracket 1 plus y, close the bracket. This 1 plus y is an OR operation, and we mentioned that for an OR, whenever one of the inputs is equal to 1, know that it gives us a 1. So this is the 1 here. So the 1 and the x, the solution here will be dependent on what we're going to put at x. If the x will be a 1, then the output will be 1. If this will be 0, then the output will be 0. So therefore, from this stage, we shall just put x. So the expression here is dependent on just the value of x. So this is what we call the absorption property. Let's appreciate duality. Number one, x plus xy is equal to x. This is true. So then x plus xy inverted is equal to x inverted. Yeah. So if we're able to invert the left-hand side of the absorption property, then we can also invert, or it's just the same as inverting the right-hand side. So equally, number two, if inverting the left-hand side would mean inverting each of the variables on the left-hand side. Then next, inverting each of the variables would mean inverting an x as well. Okay, so all these other properties that are being indicated down this side, they are simply just trying to demonstrate how we can apply, or how else we can apply the power of duality. Otherwise, there is nothing complex about these statements. So let's read number 6 and 7. The above process can be applied to any formula. So if a formula is valid, then its dual must also be valid. So proving one formula also proves its dual. Okay, let's look at the consensus theorem. Consensus theorem. Number 1, in the consensus theorem, we have xy plus x prime z plus yz is equal to, this gives us xy plus x prime z. Then number 2, we shall explain shortly using the proof. X plus y, then dot x prime plus z, we close the bracket, then x plus z equals x plus y dot x prime plus z, then we are saying this is the dual. So this is the dual. We've just simply done some changes to one, changing the dot to a plus, then again the plus to a dot. Let's look at this. In between here, there's a dot. So that dot was changed into a plus. Then we introduced brackets there. Then this plus introduced to a dot, introduced to a dot. Then we have this, the first element, the first variable, the second variable, these are the ones. Then in between here, there's a dot. That dot has been converted into a plus. Then we have this plus converted to a dot. Then the y and the z, they are in between, there's a dot. So that dot has been converted into a plus. So that's how come we're calling it the duality property. Let's look at the proof. So we're considering the first. So that the second you can easily follow through. Okay. Xy plus x prime z plus yz is equal to xy plus, we've simply, we want to show that what is on the left hand side is equal to what is on the right hand side. So we'll simply transfer everything that is on the left to the right, then start simplifying until it takes us to where we want to go. So here we have xy plus x prime z plus yz. Now here we've included x plus x prime, which was not there. We didn't have x plus x prime, but we've introduced it. It's actually equal to 1, and we know that it will still won't make much of a problem, okay? Because it's just a 1, it won't change anything. So we introduce it and expand out the brackets. So we have xy plus x prime z, then plus, we open out the bracket, we have x, y, z, then x prime y, z. Then having done that, we collect the like terms. So this moves to there, and this moves to its position. So these two interchange, okay? So after interchanging, it is clear that it reduces to xy plus x prime z. Okay, this is very, very important. So this is true. The QED here implies that this is what was to be shown. Okay. All right, so we've looked at the consensus theorem. Okay, so by the way, here you can do some simplifications, factorization, and until it brings you to this stage. Okay, let's look at the truth tables again. We're going back. Okay, we mentioned uh, uh, truth tables before. Yeah, so let's try to cement what we started. So this truth table enumerates all possible combinations of variables, variable values, and the corresponding function value. So the truth table for some arbitrary functions, let's say f1, f2, and f3 are shown here. So we have f1, f2, and f3. So these are the different input combinations. So you can have several functions that are being subjected to the same input combinations and giving out different outputs. Okay, so this is what this table is trying to illustrate here. Okay, so a truth table gives a unique representation of a Boolean function. So if two functions have identical truth tables, the functions are equivalent and vice versa. Truth tables can be used to prove equality theorems. Yeah? However, the size of a truth table grows exponentially with the number of variables involved. I think we illustrated the 2 raised to the power n arrangement that we talked about, hence unwieldy. This motivates the use of Boolean algebra. So let's look at uh, more on Boolean expressions and the table, the truth table. Unlike truth tables, expressions representing a Boolean function are not unique. We mentioned this. So these are not unique. For instance, function f gives this expression on the right-hand side of the equal sign, and function g gives this expression. These two functions give us the same output for the same input combination. So it implies that they are identical. They are identical, but they look different. The two f and g are identical, but they look different. Okay. So from the truth table, we're able to tell that indeed these two are identical. Let's look at the manipulation of Boolean expressions. Boolean algebra is a useful tool for simplifying digital circuits. Okay, but why do we need to simplify? A simpler digital circuit is much easier to build and even cheaper in terms of cost, and it consumes much smaller space, and even the operation is faster. Okay, so we have to master the manipulation of these Boolean algebraic expressions to help us design more economical, smaller, and efficient digital circuits. Okay, and not only that, this circuit is also important. This topic rather is also important to help us with the reasoning, that is the logic reasoning. Yeah, there is a kind of thinking that this topic will provoke in you, of which by the end of this topic you should be able to appreciate. Okay, let's look at an example. Here's an example. Simplify the Boolean algebraic expression shown. So we have x prime yz plus x prime yz prime plus xz. Okay, we are asked to simplify. So what do? We group these expressions. So the first two combinations are grouped like this. Then we take out the like terms. So if we take out the common factors, yes, the common factors are x prime y or x bar y. Then what remains is z plus z bar. So z plus z bar will give us a 1. This is an OR function. So plus xz, we haven't done anything to xz. Then here, x prime y dot 1, this is an AND gate. An AND gate that is drawing inputs from another AND gate and from some circuit that may be giving a 1. This is what is happening here. So we have x prime y dot 1. This dot 1, we can easily ignore it and we'll have our answer as x prime y plus xz, which is the simplified version of this expression. So if you generate a truth table for this expression, you realize that you get the same answer as the truth table for this expression. Okay. Let's continue with algebraic manipulation. Another example. This time we are proving. Prove that this expression is equal to that expression. We'll prove that the left-hand side is equal to the right-hand side. So what we do is that we write down the left-hand side, then throw it on the right-hand side and start simplifying. So after simplifying, collection of like terms, factorizing the common factors, it's definitely going to show you that x bar z bar plus y z bar is going to be reached, which is what is expected of us. Okay. The complement of a function. The complement of a function is derived by interchanging the dot and the plus, and also a 1 and a 0, and complementing each variable. Otherwise, interchange 1s to 0s in the truth table column showing f. The complement of a function is not the same as the dual of a function. Okay. So let's look at complementation. Okay. We look at an example. So here's an example. Find G with the variables x, y, and z, which is the complement of f, x, y, and z, and we have that expression. So we are asked to find G, which happens to be the complement of f. So in this case, we'll simply look at f and its complement. So G is equal to f complement equal to, we write down an expression for f, but then we have to invert everything. So inverting everything, to proceed from inverting everything would require that we convert the plus to a dot, then we split the bar. So after splitting, like in what we have here, let me just put it somewhere here. So what we have, this is a bar. It means everything is covered by the bar here. Equally this side. So if we are to get rid of this inversion, to get rid of this inversion, it means we need to say x bar plus y plus z, close the bracket, then dot, we open the bracket, and here we'll have x. Why? Because when we split the bar, we're going to have two bars on the x. Yeah, so two bars will cancel each other out and you have just x. Then here we have y bar added, not adding, sorry, we are here. We got mixed up here. Okay, the first part is x bar plus y, yes, then plus z dot, then here, yes, we have x plus, yes, x plus y bar plus z bar, and close the bracket. Okay, so this is how that expression was got. This is by use of what we called the De Morgan's laws. The De Morgan's law. Let's make sure that we understand and master De Morgan's laws. They'll be very useful in your mock examination, even the final examination. So note that the complement of a function can also be derived by finding the function's dual and then complementing all the variables or literals. Okay. Let's look at this segment, the canonical and standard forms. Canonical and standard form. Okay. We need to consider formal techniques now for the simplification of Boolean functions. Okay. So in this segment, we'll ensure that identical functions will have exactly the same canonical forms. Then we'll look at the min terms and max terms, the sum of min terms, sum of product of max terms, product and sum terms, then sum of product and sum of and product of sums. So that is the SOP and the POS. Let's begin by looking at some of the typical definitions that will make us understand this next segment. Literal, we already defined it. This is a variable or the complement of a variable. Then we have a product term. Product term refers to variables that are connected by the dot. And the sum term refers to variables or literals connected by the plus sign. Then the min term refers to a product term in which all the variables appear exactly once, either complemented or uncomplemented. Then we have the max term, which is a sum term in which all the variables appear exactly once, either complemented or uncomplemented. Okay, let's look at the min term. The min term represents exactly one combination in the truth table, and this is denoted by small letter m with a subscript j, where j is the decimal equivalent of the min term's corresponding binary combination, which is bj. A variable in m subscript j is complemented if its value in bj is 0. So whenever a 0 appears on the input part, it has to be complemented. Yeah. Otherwise, if it is not a 0 or if it is a 1, it shouldn't be complemented. For instance, let's assume three variables a, b, and c, and that j is equal to 3. So j, we said, is the decimal equivalent of the min term's corresponding binary combination. So in this case, this j3 is equivalent to 0, 1, 1. Okay, 0, 1, 1. So the corresponding min term for this input combination, which is the 0, 1, 1, the min term is denoted as a bar. Why we put a bar? Because there's a 0 appearing, just as we mentioned here. Then 1, 1 will be BC. So we're assuming that the variables here are A, B, and C. Then converting this 0, 1, 1 base 2 to base 10, it's what gives us a 3. Let's look at the max term. The max term represents exactly one combination in the truth table and is denoted by capital letter M with a subscript J, where J is the decimal equivalent of the max term's corresponding binary combination Bj. And a variable in Mj is complemented if its value in Bj is 1. Otherwise, it is uncomplemented. Okay. For example, let's take A, B, C as the variables and J being equal to 3. Then Bj will be 0, 1, 1. So if you have 0, 1, 1 as Bj, then its corresponding max term, the max term will be denoted by Mj is equal to A. So where there's 0, we just say A, and we owe all these spaces A and B bar plus C bar. So A plus B bar plus C bar. This is the arrangement of the max term, the max term. Let's look at the truth table to illustrate the two notations, the notation for min term as well as the notation for the max term. So the min terms and max terms are easy to denote using a truth table. Let's still consider three variables, which is x, y, and z. Okay, they are all following the same order. Then we have a column for the min terms and the column for the max term. So let's look at the first input combination. We have 0, 0, 0. So 0, 0, 0 in the min term will be complementing all these three inputs. So we have x bar, y bar, z bar, which is equal to small letter m with a subscript 0. This 0 means the decimal equivalent of 000. And now it's easier, like when getting the decimal equivalents of these, I normally encourage that we write these numbers 1, 2, 4. Okay, these are used for the conversions of numbers from the binary to the denary. Okay, let's assume we have this number, or these letters are representing the bits of a binary number A, B, C. Yeah, A, B, C. These are numbers. So to convert these bits into a decimal number or a denary number, we'll have to say A multiplied by 2 raised to the power 0. Then the second is going to be B multiplied by 2 raised to the power 1. Then we have C is C multiplied by 2 raised to the power 2. So further, you realize that, okay, let's close this. We're moving in reverse now. We have A, B, and C. So here, 2 raised to the power 0 is a 1. 2 raised to the power 1 is a 2. And 2 raised to the power 2 is a 4. So from these numbers 4, 2, 1, we can come up with the, whatever combinations up to 7 for the 3 inputs. So to get a number, let's say 6, to get a decimal number 6 in the binary, we'll simply say, let's come up here for the number 6 in base 10. This is equal to, we just come to this, let's say we don't know what this A, B, C is standing for, but we know that they are bits. It's either zeros or ones or whatever combination, but zeros and ones. So to come up with 6, we add 4 and 2. We add 4 and 2, and the third will have to be replaced by a 0. So if you add 4 and 2, it will mean we'll have a 1 and a 1, then a 0, and this is base 2. To come up with the number 5, or let's say, yes, okay, 5 base 10. So for 5 base 10, we look at these digits. We have 4, 2, 1. So to come up with 5, we add 4 and 1. So the one in the middle will be a 0. So we'll have 1, 0, 1, base 2. Okay, I hope this basic foundation and conversion is not difficult and you've understood it. So let's look at the min term for the first case. The first input combination is X bar, Y bar, Z bar. All these are being inverted, and we have M with a subscript 0, which is the denary or decimal equivalent of 000. Then we come to the max term. The max term inverts Where there is 0, it does not put a bar. It just writes x without any inversion. Where there is 0, it does not invert. It just puts the input there. Then the dots are all plus. So in the max term, we deal with plus, which is the or. And in the min term, we deal with multiplication, which is a dot. Okay, so now we come to the second. Oh, we didn't mention here. So x plus y plus z is equal to capital M 0. This 0 still refers to the number here in the decimal, the 0, 0, 0 in the decimal. 0, 0, 0 base 2 is the same as 0, 0, 0, 0 base 10. Okay, we move to the second row. So the second row we have 0, 0, 1. So the first two inputs will be inverted. X bar, y bar, then z is equal to M1. The 1 coincides with the 1 in the binary. Then equally on the second we have x plus y, that is under max term. X plus y. Why do we have x plus y? Because these two are zeros. So we have x plus y plus, where there is 1, we put z bar, which is M1, which is the denary equivalent of 0, 0, 1. So this process continues. Let's randomly select another. Let's select, yeah, this one. So this is 1, 1, 0. 1, 1, 0. Let's look at the min term. The min term for 1, 1, 0 will be x, y, because the x, y are not being inverted. So we have them here, x, y. Then the 0. 0 is an inversion. So z is inverted. Is equal to M6. This 6 is the decimal equivalent of 110. Then we come to the max term for the same combination. So the max term will invert all ones and let where the z remain the way it is. Okay, so here this will be x x bar plus y bar plus z is equal to M6. So 6 is the decimal equivalent of 110 base 2. I hope we made ourselves clear on the representation of min terms and max terms on the truth table. Let's now look at the canonical forms. Yeah, the canonical forms. These are unique forms. So any Boolean function can be expressed as a unique sum of the min terms, and also a unique product of max terms. That is under a fixed variable ordering. So in other words, we are saying every function f has two canonical forms. So every function has two canonical forms. The first one is the canonical sum of products, and the second is the canonical product of sums. So the sum of products is the sum of min terms, and the product of sums is the product of max terms. So let's shed more light on the canonical sum of products. So the min terms included are those mj, small letter m, such that f is equal to 1 in the row j of the truth table. So when the function gives an output of 1, those are the ones that are considered when coming up with the min terms. Whereas for the product of sums, we consider those outputs where f is equal to 0. So when f is equal to 0, those are the parts that we consider under the canonical product of sums. Let's look at some examples. The truth table for f1 abc is as shown here. So this is the truth table for a function abc, yeah, shown on the right. The canonical sum of products form for f1 is, so we are starting with the sum of products. And the sum of products form for f1 is, we have f1 abc is equal to sum of products we consider only where the output is 1. Only where the output is 1. So where are those points? We have here the second row, the third row, this is the fifth row, as well as the seventh row. Okay. So we have 1, 2, 3, 4. Okay. So the M1 is indicated, or the first one is noted by M1. Then the second one on the third row is M2. Then the third one is M4, and the fourth one is M6. Okay, so let's now consider we consider the mean term. So the input combinations, let me change to the highlighter. We move to the highlighter, yes, the yellow one. I hope you'll be able to see. So for the first one, we are considering this combination 0, 0, 1. 0, 0, 1. We said for the sum of products, where there's 0, we invert. So the first 0 will be A bar, which is what is happening here. The first 0 will be A bar, then the second will be B bar, the third will just be C. So this is what is happening here. A bar, B bar, C. Then plus, we go to the second one. The second one has 0, 1, 0. 0, 1, 0. So the first is A bar, the second is B, then the third is C bar, because the bits on the sides are zeros. So we have to invert. Then we come to the third. The third is 1, 0, 0. So the first one will not be inverted, but the second and the third will have to be inverted, which is what is happening here. Then the last one is 1, 1, 0. So the first two should not be inverted, and the third inverted. Okay? So this is how we come up with the sum of products. Now let's look at the canonical product of sums derived from the same F1. So for the sum of products, for the product of sums, the product of sums for the function f1 will consider the outputs that gave us 0. So only 0 outputs will be considered. So there is the first one, the fourth one, the sixth one, and the eighth one. So there are 4 as well. So we begin with the first. Let me convert to the field. The first, we have 3 zeros. 3 zeros means we have to add A plus B plus C without inverting. A plus B plus C, which is what is happening there. Then we put a dot. We move to the next. The next is 0, 1, 1. So the first one, we don't invert. So this would be A. But the second two, the next two, we invert them. Okay? So we have A here, it's not inverted, then plus B bar, C bar. We move to the third. The third is 1, 0, 1. So we invert for A, we don't invert B and invert C, which is what is happening here. Till we go to the last one, where everything is inverted. Okay. Then there is another very important observation here. So this observation is that the sum of products is equal to the complement or the product of sums. Okay, this is a very important observation that we need to remember. Okay, let's look at the shorthand as well as that is the shorthand representation of the sum of products as well as the product of sums. So we use these 2 letters, the sigma and the pi. So F1 ABC is equal to sigma m, then 1, 2, 4, 6, where sigma indicates that this is the sum of products form, and m, 1, 2, 4, 6 indicates that the mean terms to be included are M1, M2, M4, and M6. Okay, so this is a representative. You remember what these figures stand for? These are decimal equivalents of those binary numbers on the input combination. Then we go to the product of sums. F1 ABC is equal to pi M, open bracket, 0, 3, 5, 7, we close the bracket, where pi indicates that this is a product of sums form, and M, open bracket, 0, 3, 5, 7 indicates that the max terms to be included are M0, M3, M5, and M7. So, since Mj is equal to the complement of capital Mj for any value of j, then it implies that sigma m, open bracket, 1, 2, 4, 6 is equal to pi m 0, 3, 5, 7, which is equal to F1 ABC. So you've seen now, this is our conclusion. This is our conclusion in this kind. So the sigma function is now finally proven to be the same or equal to the pi function. Okay, then the conversions between canonical and between canonical forms. So you can replace the sigma with the pi or vice versa, and replace those j's that appeared in the original form with those that do not. For instance, F1 ABC is equal to, we have this expression here. which then yields M1, M2, M4, and M6, and it has sigma 1, 2, 3, 4, 6. This is just the same as saying pi 0, 3, 5, 7, and you have that expression, which is the product of sums. Okay. Next, we look at the standard forms, which also are not unique. The standard forms are like canonical forms, except that not all variables need to appear in the individual product, which is the sum of product, or or product of sums terms. For instance, F1 open bracket ABC is equal to A prime B prime C plus B C prime plus A C and C prime. This is the standard sum of products form. Okay, so another one is F1, which is A B C in brackets as the variables, is equal to A plus B plus C in brackets dot B bar plus C bar in brackets dot A bar plus C bar in brackets. Okay, this also is the standard product of sums form. So the one on top is the standard sum of products, and the one here is the standard product of sums. Okay, so this is very, very important. So standard forms are like canonical forms, except that not all variables need to appear in the individual product or sum terms. Okay, let's look at the conversion of sum of products from standard to canonical form. So expand non-canonical terms by inserting equivalent of 1 in each missing variable x. We actually already demonstrated something like this before on the initial slides. So if you replace x plus x bar, you are not changing anything, you're simply replacing by a 1. So then another thing we need to do is remove duplicate mean terms. So let's look at this example. F1 with the variables A, B, C is equal to, we are given this expression. So we've seen that the middle term does not have A. A is not appearing in the middle term, and B is not appearing in the third term. So we can introduce into the middle term A plus A bar, which is just a 1. It doesn't change anything, but we just introduce it there so that we show that this is a gate that has 3 inputs. Okay, so equally here on A and C, we include B plus B bar, the variable that was not seen in the expression. Then we expand out and remove the duplicates. We delete the duplicates and remain with that expression. Okay, so this is the conversion from sum of products, the conversion of sum of products from standard to canonical form. Okay, so conversion of product of sums from standard to canonical form. Expand the non-canonical terms by adding 0 in terms of missing variables, e.g. the x bar is equal to 0, and using distributive law. All this we already discussed it. So we remove the duplicate max 10. That is also one of the operations that we're going to do. Let's look at an example, very important example. So we have F1 with a variable ABC is equal to this expression. So this expression we have different, on the middle part, we don't have A, and the third, we also don't have B. So on the second stage, we've introduced A bar. Then here we're going to introduce B bar. Then on the third stage, we expand out. So we have the first term hasn't changed, A plus B plus C in brackets, then dot. Then we have the expression B. We have A. First we consider the A only without the bar. So we have the A. This A is part of this combination, A plus B bar plus C bar. Okay? So we only considered one part. We close the brackets, then put a dot. Then the next we consider this A bar. So A bar plus B bar plus C bar, brackets, then dot. It means these two have closed out this one. Then we move to the third. So on the third, we first begin with A bar plus B plus C bar, which is this. A bar plus B plus C bar, which is this. We close the brackets and put a dot, then again say A bar plus B bar plus C bar, which is this. So having come up with this, we simply delete the duplicating term. So the term that is the max term that is duplicating, we delete it and come up with this. So if you look at what we have here in this expression, the duplicate is right at the end in blue. The one that is in blue is being duplicated, so we delete it and come up with this answer. Okay, so this is where we end today's lecture. I hope it was fruitful. Let's ensure that we understand all the um, elements that we've discussed, all the points that have been highlighted in this topic, because we expect that there will be questions asked from this topic in the mock examination that we're about to be administered with. Okay, so let's end here for today. Enjoy the rest of the day. Keep on revising through your work. Best wishes. Goodbye.